Right. Right, homeostasis you know about. Homeo means the same, and stasis literally means standing. So it means of the same standing or in the same situation. Homeostasis. And you know that there's many parameters in the body that need to be homeostatically regulated. Not too much and not too little. So it's a bit like Goldilocks' porridge, isn't it? Not too hot, not too cold. It's all got to be just right. Because human cells and human tissues are very particular about the conditions they live in. And one of the parameters that needs to be tightly controlled is the amount of glucose in the blood. Glucose is the sugar found in the blood. Now we eat all sorts of carbohydrates and we eat all sorts of sugars. So you might have heard of sugars like galactose or fructose or other simple sugars. Well, all these are converted into glucose by the liver. So whatever sugar is absorbed from the GI tract, it's always glucose in the blood. Just messed my video up now. You realise your profiles will be on YouTube. Unless, of course, you don't give consent. Right, so all the sugars in the blood are converted into glucose. That is the sugar in the blood. It's always glucose. So when people talk about blood sugar, they always mean blood glucose. And give or take, roughly, we want it to be between 4 to 8 millimoles per litre of blood. That would be kind of round about the normal level. Now, if you've been out on the fells for a long walk and you've been working out and you've had plenty of exercise and you haven't had much to eat, it may go below 4 for a little while. Or if you've just had a meal followed by sticky toffee pudding followed by after eights, then it might go above 8 for a little while. But in normal situation, 4 to 8 would be what we would expect. And this is important because in diabetes, patients with diabetes, we don't want the blood sugar to go lower than 4. So what we say in diabetes is 4 is the floor. 4 is the floor. So if someone with diabetes has a blood sugar of lower than 4, we'll normally try and get it up a bit. We don't want it to be that low. Now, if the blood sugar is not homeostatically regulated, it can go too high. So hyper for high, gly for glucose, emia for in the blood. High levels of glucose in the blood. And we don't want this, because when that happens, sugar diffuses into the body tissues and messes them up. The body tissues become a bit like, you know, that crystalline pineapple stuff you get that tastes really nice. But it's crystalline because it's full of sugar. We don't want that. It will damage body tissues if the blood sugar is too high. This is why we get a lot of long-term complications in diabetes. So if patients with diabetes are chronically hyperglycemic, if the blood sugar is high over many months and years, then they're more prone to quite a few of the long-term complications of diabetes. So we don't want the blood sugar to be too high. If the blood sugar goes low, hypoglycemia, emia in the blood. If it goes low, that's bad news as well. Because as you probably know, in all the cells of the body, you have a nucleus, and you'll have a few hundred to 1,000 or 2 of these sausage-shaped organelles, these sausage-shaped structures. Remember these ones? And then enfolded in a membrane. Yeah. Yeah. The mitochondria, which are the powerhouses of the cell. All the energy that cells make is made in the mitochondria. We don't get any energy from other sources. And all living processes need a constant supply of energy to fuel the life-giving processes. We always need the energy. So what happens in cells is that glucose combines with oxygen, glucose and oxygen, and it's that which produces energy. The glucose is burnt in the oxygen to give us the energy. And as you probably know at the same time, this results in the production of water and carbon dioxide. This needs to go on inside the cells to produce the energy. And obviously, if we're hypoglycemic, there's not going to be enough sugar to do that. Not enough energy. Now that's okay for some tissues. Some tissues can work without glucose. They can use fats. They can use fatty acids as their fuel supply. But the brain's not very good at that. The brain is an obligate glucose user. The brain has to have glucose. So if someone becomes hypoglycemic, the brain can't produce energy in the mitochondria, therefore the brain stops working. And make no mistake about it, these people will die. Hypoglycemia is a life-threatening condition. So we always have to be careful how we use insulin, because if we give too much, patients become hypoglycemic, and there is a real risk that they're going to die, because their brains will stop producing energy. Can you see why 4 is the floor? You're not going to die with a blood sugar of 2. You won't feel very good. But can you see it's on the way down? And below that you are getting to very, very dangerous levels indeed. That's why we say 4 is the floor. We don't want it to go lower than 4.
John, which is the most dangerous situation to be in, having too high or too low?
Right. Hyperglycemia causes long-term complications over weeks, months, years. Well, potentially over days. If you're hyperglycemic, you're more prone to infections straight away and things like that. But most of the complications are very long-term with hyperglycemia. Whereas hypoglycemia can kill you in half an hour.
But are there any, if you have hypoglycemic crashes fairly regularly, is there any long-term detriment because of that?
That's a very good question. The answer is probably, yes.
Oh, goody.
Yes. Yes, the answer is probably. But the evidence for it is not strong.
Right.
But the patients feel so bad, we want to avoid it anyway. But yeah, chronic hypos, yes, probably does have some long-term deleterious effect, but it's not well evidenced.
I know certainly when I've had really bad crashes, it can take me a week, 2 weeks
To feel normal again.
Yeah. So
Yeah. Yeah. Yeah, I mean, it's not really something to be overly concerned about in long-term complications, but there probably is something.
Yeah.
But it'll follow a distribution curve the same as everything else. You know, some people have them and not have adverse effects, some people have them and will have adverse effects. Yeah.
With the hyperglycemia, John, what are the sort of side effects? Is it like your eyes and your peripherals?
Yeah. The main thing with hyperglycemia is that you wee a lot.
Right.
That's the main immediate feature. You get what you call an osmotic diuresis.
Is that why you always feel thirsty?
Yeah, because you're dehydrated. Yeah.
Is it that's because you're trying to get the sugars out?
Yes.
Right.
Osmotic diuresis, yes. When the sugar goes into the nephron, it attracts water because the glucose is osmotic. So you can wee huge amounts, and of course that makes you chronically dehydrated and that makes you chronically thirsty. And the other thing that happens is if the mitochondria can't use glucose for their fuel supply in the muscles of the body, then they have to use something else. And the something else they use are fats and proteins. So you get weight loss. So that's the classic triad for the presentation of diabetes, those 3 things. Polydipsia, polyuria and weight loss. Any of those 3 we should automatically do one of these doodahs and test the blood glucose levels. Yeah?
With type 2 diabetes, why is it that you don't get so much hypoglycemia, but then you can get patients like, I know somebody that gets a lot of hypoglycemia attacks, but they're still type 2.
Right, okay.
It doesn't seem to make sense because
Yeah.
the normal pattern is
Yeah.
that you don't get hypoglycemia.
Well, with type 2 you certainly get hyperglycemia with type 2 diabetes. The reason that you're more prone to hypoglycemics with type 1 is not because of the diabetes. That causes hyperglycemia. It's because of the insulin. It's the insulin that lowers the blood sugar levels dramatically, as hopefully we'll see. Now with type 2, some patients with type 2 diabetes do take insulin. Therefore, their risks of hypos are just the same as someone with type 1. More typically, patients with type 2 diabetes take oral hypoglycemics. They take oral medication to lower the blood sugar levels. Now, some of those, like gliclazide, can lower your blood sugar quite dramatically. Others, like metformin, aren't supposed to lower your blood sugars dramatically, but actually they do. People that take metformin, the books say they don't, right? But people that take metformin for type 2 diabetes do have hypos. And they do feel pretty bad. Now, they're not crashing hypos like you would get with insulin. They're not going to die from it, I don't think. But they certainly get hypos. But with some of the other hypoglycemics, like gliclazide, you can get quite bad hypos.
No, they're on metformin, so that's
Yeah. So the answer is that metformin is not supposed to cause hypos, but it does.
right.
Yeah, excellent questions. Good. Yeah, so anyone who's weeing a lot, thirsty a lot, or losing weight, and hasn't got an obvious explanation, then we need to start thinking about their glucose status. And of course, it's very simple to test the glucose levels in the blood. So we don't want hyperglycemia, we don't want hyperglycemia, we don't want hyper or hypo. What we want is euglycemia. Euglycemic means that the glucose levels in the blood are normal. That's what we want. We want them to be euglycemic. Can you see why this is a homeostasis outing, isn't it? We don't want hypers, we don't want hypos, we want euglycemia. So, how is that achieved? Well, some of you have come across this one before. Remember him or her? Pancreas. Now the pancreas is described as an organ with a head, a body and a tail. And it's here. Put your hands up there. Right, so the head of your pancreas is there towards the middle and right side. And then the body is over there and the tail is over there. So it's a head, a body and a tail. And of course, what most of the pancreatic cells do, most of the pancreatic cells produce digestive enzymes. So these ducts here, these pancreatic ducts, digestive enzymes go down here, come out here, and of course that goes into the first part of the small intestine, which is the duodenum. There's a few bile ducts to complicate it, but that's basically what happens. That's good because it means you can digest proteins, it means you can digest fats, it means you can digest carbohydrates. Pancreas produces all sorts of digestive enzymes, which of course is fairly boring. But what is very interesting about the pancreas is it's very spotty. Distributed throughout the parenchyma, throughout the tissue of the pancreas. There's lots of these little islands of tissue. And when you look at them in a microscope, It's like you're flying over a sea of pancreatic cells, and then from time to time you see these little islets. These are called the pancreatic islets. And if you're, I don't know, should we say about 35 or over, you probably learnt the term the pancreatic islets of Langerhans. Of course, you may be young and know about the pancreatic islets of Langerhans, but have an old-fashioned teacher like me. So the pancreatic islets, or the pancreatic islets of Langerhans. Langerhans is a guy's name, Paul Langerhans, I think
And
his
is
name
that
is.
them dots?
Yeah, that's these dots.
Why did they call it that then?
Well, Langerhans discovered these pancreatic islets and said, oh, I'm going to call them the pancreatic islets of Langerhans. It's a bit like Stanley walking through Africa. Oh, I think we'll call this Lake Stanley, you know. Certain amount of egotism there, perhaps. Or maybe it wasn't him, maybe it was his mates thought it was a good idea. Now, there's about 1.5 million of these little islets in your pancreas. About 1.5 million of them. So there's loads of these things, but they're very small. Pancreatic islets. And if we look at one of the islets magnified a bit, imagine that's a pancreatic islet, then we find that there's two main types of cells in pancreatic islets. Round about the outside, there's a type of cell called alpha. Alpha cells. And that's the Greek letter alpha. So the alpha cells are round about the outside of the pancreas primarily. But there's more cells inside called beta cells. And that's the Greek letter beta. So there's alpha cells around the outside of the pancreatic islets and beta cells in the middle of the pancreatic islets. And between the two of them, these are the main cells that control the amount of glucose in the blood. So first of all, let's think what happens if the glucose levels start to rise. So you have something to eat, the carbohydrates and the sugars are digested, they go into the blood sugar level is going to rise. And the beta cells have a good blood supply, so the beta cells are able to sample the blood which is going through the beta cells. They can sample that blood. And the beta cells are so clever, they can detect when the amount of glucose in the blood has gone up. In other words, the beta cells detect hyperglycemia. They detect increases in blood sugar level. So when the blood sugar level rises, that's detected by the beta cells, and in response to that, the beta cells produce insulin. So when the blood sugar level rises, it's detected by the beta cells, and the beta cells produce insulin. So can you see now, as well as having a lot of sugar in the blood, we've got insulin in the blood as well. Because the pancreas, all the digestive enzymes in the pancreas, leave via these ducts, and anything that produces a product which leaves via a duct is called an exocrine gland. You heard that term? Exo, to exit. So if the product leaves via a duct, we call that an exocrine product because it is exiting the gland. But the insulin is not like that. The insulin doesn't leave the pancreas via a duct, it leaves the pancreas via the venous drainage of the pancreas. It goes straight into the blood. And whenever a product is released straight into the blood, the term we use for that is endocrine. So the beta cells are endocrine. They are releasing the hormone insulin directly into the blood. So we've now got more insulin in the blood, which is good, but so what? Well, the glucose is a simple molecule. Glucose is actually only C6H12O6. So a glucose molecule only contains 24 atoms. Quite a small molecule. And it's this kind of shape. It's shaped like this. It's a hexagonal shape. And glucose is a highly soluble molecule. It's highly soluble. Because it's small, it's water soluble, it dissolves in the watery tissues of the body. And because we've just had something to eat that contains carbohydrates, we've got loads of these things. Glucose floating around in the blood, glucose floating around in the tissue fluids. Lots of glucose molecules. Now what insulin will do, one of the things that insulin will do, is it will tidy all these individual glucose molecules up. So the first thing it will do is it will tie them all together into a big long string. Like this. Hundreds of units long, it ties them all up into a big long string. And that big long string, that polymer, it's a polysaccharide of glucose molecules. It's a big long molecule like starch. The glucose is converted into glycogen. So this is called glycogen. So the glucose is converted into glycogen. Big, long polysaccharide molecule. And what the body does is it stores this glycogen, and it stores it in two places primarily. It stores it in the liver, and it stores it in the muscles. So it's stored in the liver and in the muscles. So if all these glucose molecules are now forming a glycogen molecule, can you see all the glucose molecules are no longer in the blood? They're all neatly tidied away in relatively insoluble form, and they're stored in the liver and they're stored in the muscles. What's that going to do to the amount of glucose in the blood? It's going to reduce it, isn't it? So can you see the initial problem was hyperglycemia? That hyperglycemia was detected by the beta cells in the pancreatic islets of the pancreas. As a response to the hyperglycemia, the beta cells produced insulin. The insulin facilitated the conversion of glucose to glycogen. It took the glucose from the blood and tissue fluids, converted it into glycogen, and swept all that away neatly into the liver and the muscles. Therefore, the amount of glucose left in the blood is reduced. That's one thing the insulin does. That's one of its hypoglycemic mechanisms. one of the ways it lowers blood sugar levels. And that's also quite a neat trick, because we've just had something to eat today, but do you think there'll be any food tomorrow? Well, yeah, obviously, because there's a packet of biscuits in the cupboard, isn't there? But of course, there might be no berries or foraging crops available tomorrow. Maybe the young men won't make any more kills for the next month. So in a basic tribal situation, and you see it's absolutely vital, or any time where there's not enough food readily available, or necessarily available, it's absolutely vital that we store enough for the next couple of days, whenever we can. And that's what the body does, it stores it. But it also gets rid of it, so we're not getting the complications of hypoglycemia. But can you see already that if someone has diabetes, if someone has type 1 diabetes, what actually happens in type 1 diabetes is the beta cells are actually destroyed. In type 1 diabetes, the beta cells are destroyed by the body's own immune system. It's a terrible mistake. It's called an autoimmune disease. So in type 1 diabetes, the sugar can go as high as you like, and you'll get very sugary blood going through the pancreas. But if all the beta cells are dead, can you see there's nothing to detect that hypoglycemia? And there's nothing to produce the insulin to combat that hypoglycemia. That's the problem. It's a terrible mistake. The immune system, over the course of a couple of years, completely destroys all of the beta cells. Terrible mistake, but that's what happens. Now, what we have lying around inside cells, as well as the mitochondria, lying around inside cells, there's donut-shaped structures, or polo mint-shaped structures, not like a jam donut, you know, a proper donut with a hole in it. So they're lying around inside cells. And also, on the surface of cells, there's a special protein, and that protein is an insulin receptor. So there's insulin receptor proteins on the surface of cells. So when the blood sugar is too high, in the normal situation, the beta cells are going to release insulin. Now, insulin is a molecule with a particular shape. Let's imagine it's round. It's actually a short protein. It's made up of a chain of about 51 amino acids. So the insulin's been released, and we know that the insulin has already facilitated the conversion of glucose to glycogen. But also, the insulin fits into the insulin receptors on the surface of many cells. So the insulin fits onto the insulin receptors. This is the lock and key idea, isn't it? So the key would be the insulin molecule, and that's fitting into the lock, which is the insulin receptor. So that fits into there, which is all very nice and snug. But when insulin fits into the insulin receptor, actually this insulin receptor goes all the way through the cell membrane to the other side. It's actually what you call a transmembrane protein. It goes all the way through. And when the insulin combines with the insulin receptors, this combination sends messages off to these polo mint-shaped molecules that are lurking around inside the cytoplasm of the cell.
Are they polo-shaped ones?
Well, the polo mint-shaped ones are actually called GLUT. And that stands for glucose transporters. They're called glucose transporter molecules. But at the moment they're not, they're completely useless because they're inside the cell. Sitting around doing nothing inside the cell. But when the message comes that the insulin has arrived in the insulin receptor, that message goes inside the cell and it sends these donut-shaped molecules, these polo-mint-shaped molecules to the cell surface. So what you end up with is one of these round molecules with a hole in it on the cell surface. So it floats on the cell membrane on the surface of the cell. And what that means is that these individual glucose molecules that are kicking around here so we go back a bit. Before these glucose molecules arrived, before the glucose transporter molecules arrived, the glucose molecules would try to get into the cell. They would try to diffuse into the cell. But the problem is they can't, because the cell membrane won't let them in. Why won't the cell membrane let the glucose molecules in? Because after all, the mitochondria needs the glucose molecules to get in.
Too big.
No, they're not too big. They're relatively small molecules.
Because it's not soluble.
Yeah, that's right, that's right. The answer is that the cell membranes are made of lipids. Cell membranes are made of fat, basically. Cell membranes are made of phospholipids. And that means that the water-soluble glucose molecules can't diffuse through the fatty cell membrane, because fats and water don't mix. So you know, if you've got some water and you pour some olive oil in, it just forms globules, doesn't it? Doesn't mix. So because the glucose molecules are water soluble, they can't diffuse through the fatty cell membrane. They're stuck on the outside. But now, can you see a hole has arrived? That makes sense? A hole has arrived. And that hole is sitting on the top of the cell membrane. So now the glucose molecules can get through the hole, that is the glucose transporter molecule, into the cell, going to the mitochondria where they are required. You need the glucose you need the insulin to transport the glucose into the cells. Before that, the glucose waited without, while the mitochondria waited without glucose. So the glucose was outside, couldn't get in. Even though the mitochondria wanted it, glucose couldn't get in until this hole was provided by the glucose transporter molecule. But that only happened because the insulin hooked up to the insulin receptor. Now, as a result of this, the glucose will pour through the glucose transporter molecule into the cell, and the mitochondria will be happy. They'll make all the energy they need now. This is the great irony in diabetes. In diabetes, type 1 anyway, when you don't have the insulin, you've got these glucose transporter molecules inside the cell doing nothing. You've got this massive glucose outside, you've got great hyperglycemia outside, but you've got no glucose inside. So you've got masses of glucose outside, no glucose inside. So you've got the glucose outside causing the complications of hyperglycemia, but you've not got no glucose inside to fuel your metabolic processes. So the mitochondria is obliged to use fat and proteins to make its energy. You need the insulin to get the glucose into the cells. So can you see now we've got loads of glucose inside the cell, much less glucose in the blood because the glucose from the blood has gone into the cell, therefore with lower blood sugar levels. Does that make sense?
Does it tie it in the strings first and then pull it?
No, it goes through as individual soluble glucose molecules. So there's two separate mechanisms via which insulin is lowering blood sugar level. One is it forms these big long strings of glycogen and stores them away for tomorrow. The other one is it transports the glucose molecules through the cell membrane into the cytoplasm of the cell. So it's two completely separate mechanisms. But they both have the same effect. They both lower blood sugar levels. And when you give insulin, blood sugar levels are lowered quickly and dramatically. This is a very effective mechanism. So the original problem was hyperglycemia. The blood sugar was rising because we'd eaten. So the insulin brings it down via those two mechanisms. So as a result of the production of the insulin, can you see we can now restore euglycemia as opposed to having ongoing hyperglycemia? Do you want to tell that story to your next door neighbour?